Hello, welcome back to a review of Chapter 8. So hopefully this review will help you with your projects and also with your Chapter 8 assignments. They're not going in any specific order, so it will definitely help for us to kind of have to put things together and which parts of Chapter 8 are we talking about. So in a survey of 1,500 U.S. random adults conducted in 2009 by the Financial Industry Regulatory Authority, 810 said they always pay their credit cards in full each month. Verify the requirements for constructing a confidence interval for the population proportion of U.S. adults who pay their credit cards in full each month. Give explanations with context. Okay, so we're talking about proportions, so that's important. So that means we're going to be using the formula here that we've been using in class for proportions. This is 8.3 in our class. And here are our requirements. So the first is, do we have a random sample? And a random, the U.S. random adults. So yep. The second thing is independence. So if we take 20 times our sample size of 1,500, which would be 30,000. We definitely think that's less than all of the U.S. adults. So in the U.S., so yeah. And the third thing is the normality check. And for proportions, the normality means the N times P times Q, or N times P times 1 minus P. In this case, it's P hat, because we don't know what the population proportion is. So either you're using Q or 1 minus P as your symbols. Has to be greater than or equal to 10. So N is 1,500, and P hat is 810 out of 1,500 said yes. So I am going to Desmos, and I'm going to find what P hat is, and it's 0.54. And we're just reminding ourselves that these are the central limit theorem requirements that we're looking at. So 0.54 times 1 minus 0.54, and we're going to figure out what that is in Desmos. So that is 372.6, and that's definitely greater than 10. So we have met all of the requirements. That's good. Okay. So it says construct a 98% confidence interval for the proportion of U.S. adults who pay their credit cards in full each month. We're going to show the formula and substitution. So the formula is P hat plus or minus the critical Z value of alpha divided by 2 times the standard error, and the standard error is P hat times 1 minus P hat all over N. So we need to know alpha, which is 1 minus the confidence level of 0.98. So alpha is 0.02. Alpha divided by 2 is 0.01. And we have a number of ways to find Z of 0.01. That is a common Z. It's a common value for Z, which means that we can use our table in our formula packet and go all the way down to the bottom where it's for 0.01, which is right here, and going all the way down to the bottom. I did recommend writing the alpha values down here. And 0.01 is 2.326. Now, we can also find that in Desmos. And I'm going to give you just a retraining on that. So there is a tab in Canvas that's called Critical Z-Value Scores and Normal Curve. So in here, you're going to be able to find the, we don't want to know the area to the right. We want to find the area to the left of it. So we want to find a Z-score down here that goes with the probability. So we're going to open that. And we want to have 0.01, and it doesn't matter which one you do because Z is symmetric. So 0.01, and it tells you it's negative 2.326, but remember that they're symmetric, so we're going to use the positive of that. So now to fill in this is going to be 0.54 plus or minus 2.326. And then the standard error, which is the error bound. This is part of our error bound margin. This is our error bound of the proportion right here. And so this is 0.54, 1 minus 0.54 all over 1,500. So let's go ahead to Desmos and find the error bound of the proportion in Desmos. So we have 2.326 times 0.54 times 1 minus 0.54 all over 1,500. Oh, oops, that's the square root. Okay, so the square root of p hat times 1 minus p hat over n. So our error bound of the proportion is 0.0299. So that means our lower bound is subtracting 0.02993, and our upper bound is adding 0.02993. So our lower bound is 0.51007, and the upper confidence value is 0.56993. So there is that. Now I'm going to show you, and I'm putting this into, I want you to be able to fill in the formula at least, but you can always check your work and do your confidence intervals using the little computer program in Desmos. So if you go to Desmos, and hopefully you've been saving these in your own Desmos when you click on my link in Canvas. So there's the one that's confidence interval for means, and then I'm going to pull up the one that's the confidence interval for proportions. So we're going to put in our sample size was just 1,500, and then our p hat is 0.54. And then for the confidence interval, the only other thing we need to do is go in and put our alpha. Now remember, alpha is 0.02. Desmos will take care of dividing by 2 for the confidence interval. So then all we have to do is go down, and we're going to open the tab right here. This is confidence interval for C equals 1 minus alpha. And we scroll down, and there is the same lower bound and upper bound that we came up with. Now, question number 2. A medical researcher wants to construct a 99% confidence interval for the proportion of knee replacement surgeries that result in complications. An article in the Journal of Bone and Joint Surgery suggested that approximately 8% of such operations result in complications. Using this estimate, what sample size is needed? Okay, that's what they want, is sample size is needed so that the confidence interval will have a margin of error of 4%. So we need to go to our formula packet or to your note sheet, but our formula packet has the formula for sample size, and we're dealing with proportions, so there's two to choose from. One is when we have a prior estimate, and one is when we do not. So this is proportions, and it does say that they have a suggested value. So they're saying that we can probably use from previous data 8% as our p-hat. So we're going to use this formula because we have a suggested estimate. So n equals p-hat 1 minus p-hat times z of alpha divided by 2 over the error, all of that squared. So we have 0.08 times 1 minus 0.08. This is what they told us from prior data. And then we have to find the z that goes with our confidence. So our confidence level is 99%. So alpha is 1 minus 0.99. So alpha is 0.01. So alpha divided by 2 is 0.01 divided by 2, which is 0.005. So we need to find z of 0.005. So I'm going to first look on my table because that's the easiest and quickest. So I do have a 0.005. That value for z is 2.576. So 2.576. And my error, they said, is within a margin of error of 4%. We always turn that into a decimal value. And then that's squared. So we're going to go to Desmos to enter this. We have 0.08 minus 0.08. And then we have 2.576 divided by 1 squared. Okay. So it says our n should be 305.25. And we have to remember something, going back to our paper here, that when we do sample size, we always have to round up. Always round up. It doesn't matter if we would naturally round down, but sample size always rounds up, so you always have enough in your sample. Because if we rounded down to 305, it wouldn't technically be a 99% confidence. So we have to round up to 306. Next. Let's go. The following are the numbers of calories in a random sample of 10 slices of bread. It says verify the requirements of constructing a confidence interval for the population mean number of the calories are met. Give explanations with context. So the first is, do we have a random sample? And it does say we took a random sample, so that's a check. And then we're checking for independence. Because I'm sampling without replacement. I sample a slice of bread, I can't resample it. So 20 times 10 is equal to 200. And I definitely think that there are more than 200 slices of bread out there. And then the third requirement is the normal requirement. And so I'm going to first look to see my sample size. Well, my sample size is 10, which is less than 30. And it doesn't say that it's normally distributed already. So this is probably the first time you've ever seen a normal probability plot. More than likely, I will not be putting any of these on the final, but I did want you to see this. We've always done examples where our sample size has been bigger than 30. But if it's not bigger than 30, we're going to give you this normal probability plot, and you're just looking to see if it appears normal. So normal plot appears linear. Follows this line. So we have met the CLT for means. Now it says interval for the population mean number of calories. So we have data, raw data. So we have to go in and find some information about our sample. So we're going to go to Desmos to do that. So I'm going to go and add a table and put my data in. And then I need to find the mean. Of X1 and the standard deviation of X1. And it's a sample, so we don't use the P. So our sample mean is 59.2. I'm just going to double check my data points. 70, 67, 70, 62, 52, 48, 49, 51, 55. Yeah. And then our standard deviation, S, is equal to 9.102. You should be trying all that on your own. So again, I want you to show the formula. So we're going to be using this formula with the T formula because it's 8.2. We don't know the population mean or standard deviation. So it's X bar plus or minus T of alpha divided by 2 times sample standard deviation divided by the square root of n. So X bar is 59.2 plus or minus. We'll find our T in a minute. S is 9.102 divided by the square root of 10. Okay. So alpha is 1 minus 0.98 or 0.02. Alpha divided by 2 is 0.02 divided by 2 is 0.01. And so we're looking for T of 0.01, comma, up here, my degrees of freedom is n minus 1, or 10 minus 1 is 9. So I'm looking for the T of 0.01, alpha divided by 2 is 0.01, comma 9 for my degrees of freedom. And we should be able to use our table for that. So 0.01 is right here, and we're going to the row that is degrees of freedom of 9. And so we should be using 2.821. And then we are going to go to Desmos and type that in and see what we come up with. So we have 59.2 plus, actually, let's just do our error bound of the mean, 2.821 times 9.102 divided by the square root of 10. So there's our error bound, 8.12. So we're going to have our mean 59.2 plus 8.12 and 59.2 minus 8.12. So our lower bound is 51.08 and our upper confidence value is 67.32. Now, we could go to the Desmos calculator and calculate it there. So we can put in our N, which was 10. Our sample mean was 59.2. Our sample standard deviation was 9.102. And then we're going to scroll down to our alpha. And our alpha was 0.02. And then we can go right down to our confidence level. And it was already open. So you would just look to see, open the confidence level interval, and then scroll down. And there are the same values that we came up with, the lower and the upper. Okay. And then question 4 is efficiency experts study the processes used to manufacture items in order to make them as efficient as possible. One of the steps used to manufacture a metal clamp involves the drilling of 3 holes, and an efficiency expert wants to estimate the mean amount of time that this step takes. The sample standard deviation is 10 seconds. How large a sample must the expert take so that a 99.5% confidence interval will have a margin of error of 1.5? So we're going back to our formula packet, and we're looking at sample size for mean, and the parentheses are off. So this whole thing is in parentheses. So it's the critical Z value times the sample standard deviation divided by the error, and that whole fraction squared. So it said how large a sample. So that's how we know it's a sample size. Okay, so we know our error wants to be within 1.5 seconds. And our sample standard deviation is 10. And then we have to find our critical Z. So alpha is 1 minus 0.995, which equals 0.005. So alpha divided by 2 is 0.0025. So we need Z of 0.0025. Let's see if this is one that's in our sheet here. It is up here, 0.0025. That's this one down here, 0.0025. So it's 2.807. So we can go to Desmos, calculate this, and we have parentheses 2.807 times 10 divided by 1.5. And then we need to put that to the squared. So it's a sample of 350.19. And going back to our paper, remember it's sample size. So we always round up. So we always round up. So as we need a sample of 351 items, clamps, so that we can test them. Hopefully this little worksheet has given you some good review on the concept of chapter 8. Catch me back for another video.